Today on Dino Dilladon, I have an interesting laser to show you guys, and that is a JenLas D2.3 manufactured by Jenoptik. So this is a 532 nanometer laser capable of producing 2 to 3 watts of output, and it's a DPSS laser that falls underneath the category of what we call a thin disk laser. What's a thin disk laser? Well, I'm glad you asked, because in this off-the-cuff video, I intend to tell you and show you all about thin disk lasers. So let's literally get into it. The easiest way to explain what a thin disk laser is to simply show you, and the thin disk is in the back of this unit, held in by normally 4 screws, but I took out 2 to expedite the process. Go ahead and jump right in to removing laser bits. Alright, be very careful. You want to have a dust-free place for this. Laser optics don't like dust. And here we have our thin disk. So let's take a look at what we have here. No, this is a terbium doped yttrium aluminum garnet. That's YB colon YAG instead of the normal neodymium doped yttrium aluminum garnet. You'll notice that this is not a transparent crystal, but it's a little flat, opaque, shiny looking block. Well, this operates a little bit different than the normal neodymium doped yttrium aluminum garnet that you might be familiar with. And the difference in operation is that it's not a pass-through optical device. It is a reflective optical device. Let me explain that. So instead of the laser light going through the gain medium, it actually enters in and reflects off the same surface. Reflect is a poor word of saying how it works, but we'll stick with it in this case because it's actually a conversion process that also goes on as well. So in this setup, we got the pump laser light that comes in, reflects on the surface, gets converted, and then bounces off. So in this case, we have a 808 nanometer pump diode inside of this unit, and that gets converted over into the 1064 nanometers. It gets frequency doubled in by lithium perborate on the inside of the unit. More about that later on. But yeah, no, this is not a pass-through laser optic. In fact, it works a little bit more like an OPS chip does in an optically pumped semiconductor, where it actually sends the laser light off the same surface as it does receives the pump laser light. Pretty interesting. Now let's take a look at the back of the laser head where the thin disk sits. We have 2 lenses. These are positive meniscus. That means that they magnify. They don't spread out the light. And they're for focusing the output into a little dot. Now, let's take a look. See what we have here. We have a lens here on this side. That's the side that the pump laser light comes from. So 808 nanometer laser light comes out this way, hits the thin disk, bounces off the thin disk after it's converted into 1064 nanometers, and goes through this optic right here and back inside of the laser. Now that you've seen that, how that all works, I'm going to go ahead. I'm going to put the thin disk back on the back of the laser head. Alright, I'm going to pop the cover off the laser now so you can get a really good idea of what else is going on the inside of this laser head. Sadly, this laser is not in the best of condition. In fact, when I got it, the cover wasn't even attached. The screws were missing, and I needed to make a new silicone seal for the top. This laser was full of dust, had to clean it out, but we got some decent output out of it. About a watt. So wish I got more. Some alignment still might solve that, but that's where I'm at right now. Carefully pop the top of the laser off. There we go. And you can see, did a nice job of making that seal. The silicone myself looks nice. I'm happy with how it turned out. Alright, so this is the inside of the laser head. We're going to start back here. So we got the pump laser diode right here, and that produces about 15 watts of 808 nanometer laser light. We got 2 electrical connections right here. You can see how they're connected to the outside terminals at positive and negative. Our output is towards the back of the laser. So here's where the emitters are, and on the front of the emitters there's a FAC lens, which is for fast axis correction. It gives the output a little bit more of a uniformity, and the dot is a little bit more concentrated on the thin disc in the back. But the pump diode laser light comes in this way, goes through that one positive meniscus lens in the back, and gets focused down into a little itty bitty point on the thin disc. A thin disc then converts it over from 808 nanometers into 1064 nanometers. And then that laser light comes through this way. It's another positive meniscus lens, and then gets beam shaped to travel along the inside of the laser this way, and then hits the optic here in the front. So this optic in the front, you can see it right there, is what we call the output coupler. And the output coupler has a couple of points of adjustment on it if you're trying to do the optical alignment on one of these lasers. Firstly, there is this adjustment screw here, which will take and tilt that optic back and forth like this. And the second set of adjustments you can do is with these screws here holding that whole optical assembly on. You can kind of finagle it around as needed. Inside this container right here is actually a little desiccant pack. It's pretty neat. The laser light hits the output coupler, gets reflected off the output coupler, comes back into the laser this way, and goes through this little crystal right here. This is LBO, lithium triborate, and that's for the second harmonic generation. And behind that is another mirror optic right there, which is probably the high reflector. Although, to be honest, the actual thin disc itself and that optic might be doing their own high reflector purposes. This one, of course, being the high reflector for the 1064 nanometer resonator portion, and then this being the high reflector for the 532 nanometer second harmonic generation portion of the resonator. So we got a lot of things going on. Looks like the silicone I mixed up is still leaking a little bit. Weird. That's okay. Sometimes we don't do things quite right in the right ratios, but it beats having no seal at all. So I'm gonna run with it. Oh yeah, let's talk about the adjustment for that real quick. So the lithium triborate second harmonic generation crystal has a couple of optical adjustments itself that you might be aware of, or might want to be aware of if you're working on one of these lasers yourself. We got this adjustment screw right here. That sets the angle of tilt on the LBO like this. And we have two screws right here that have little cutouts. So you can see that cutout here, a little bit of a cutout here around this screw, which allows this whole optical mount to rotate like this. The other thing to note is the LBO needs to be held at a specific temperature, which is normal for a lot of the LBOs and lasers like this. There is a little thermoelectric cooler underneath the LBO right here, and that's for warming the LBO up to its proper temperature. They like to run at a specific temperature best, so you'll often see that in DPSS lasers, a little heater, whether it's a PTC, a resistive element, or a TEC that they run for a heater. It's usually somewhere in there. Got a couple of wires right here. Two of those wires will be for the NTC thermistor, which gives us our feedback for how hot this optical mount is. And then these two wires right here, which are for the TEC on the bottom. So, yeah. Just to recap, 808 nanometer laser light is produced here, gets sent to the back of the laser, gets focused down into a point, hits the thin disc. That thin disc gets, it converts the 808 nanometer light over to 1064. That 1064 nanometer light gets beam shaped and sent out this way, bounces off this optic here. That then travels this way through the second harmonic generation crystal, bounces off this mirror here, gets converted over into 532 nanometer laser light, and then it travels out through the output coupler. So it's only the infrared that gets bounced off this. But that's how this thin disc laser works. Now, of course, you want to see it work, right? First, you want to see it work. We'll have to go and do that right now then, eh? That's a simple enough task. So I'm going to put the cover on while I do that, make my connections, but that'll go pretty quick. First thing we need is something to cool the laser. So this has a, I need to back the camera up a little bit too. Can I zoom out more? I can. Okay, so this has a pump laser diode in here that takes 40 electrical watts, about 2 volts at 20 amps, and it's not very efficient, so we're going to need to get rid of the heat somehow. So I got my little thermoelectric cooler here. I'm going to go ahead and put some thermal paste here on the bottom of the laser head, where the pump diode is. That'll do for our test purposes. Set that down on the cooler. I'm going to go ahead and move the camera real quick. We'll come right back to this. Much better. Now you can actually see what I'm doing. All right, let's go ahead and start connecting up the necessaries for this laser. Start with power. I'm going to use a 20 amp lab power supply here. Forbids to reverse. Take off the wire here. So that's just to short out the pump diode while it's not in use to prevent ESD from damaging it. Very important. Alrighty. That will use that. Good enough. And on the positive side, I have here a piece of copper wire. The resistance of this is 10 milliohms. I'll be using this as a current shunt to read the current going to the laser head. Oh, you'll see that a little bit more in detail. Let's just follow along. That way I don't have to read the power supply. Just pay attention to what I'm doing right here. And you guys can pay attention to what I'm doing right here. All right, cool. Got that all set up. Let's go ahead and connect the meter. That'll work. All right, so our millivolts are going to be equivalent of what our wattage, amperage is going to be going into the laser head. So 10 millivolts will be 1 amp and so on and so forth. All right, power supply is connected. We're also going to need to take control of the LBO and the crystal temperature. So I'm going to use one of the laser power supplies that I made that has that feature. I'll take that. And I'll put up the pinout of the LBO and of the thermistor online so that way you have it. It'll be in this video, probably at the end. Don't worry, it will be there. So that way you can hook this up all on your own if you have one of these wonderful lasers. All right, that looks good. We have control over cooling here. Yes, cool. We're gonna need to connect power up to these wires. That'll help. I bet it likes electricity. Nobody goes off the cuff like Xenodilodon. All right, it's time to start flipping some switches. So let's flip some switches. First of all, let's set the meter on so we can see what our current is going into the laser. 0 volts DC, excellent, cool, awesome. Let's turn on the thermal coolers so that way we can cool down the laser head. Excellent. That's going as planned. No smoke yet. Good. Why aren't we getting activity lights here? Uh-huh. That's right, that's right. Maybe that connection in the block doesn't work anymore. That's why we make redundant connections. Uh-huh. Redundant connection activated. Now we have light. Very good. All right. We should be good to go. I see no problems. Main power supply on. Let's bring up the current. Yeah. All right, we should be at 10 amps right now. We are. All right, cool. Go ahead and take off the tape on the output aperture of the laser. We get a dot. Let's adjust the camera so you can see the dot. All right, so let's set the temperature of the LBO. See if we can get more power output. Gonna go ahead and set the laser power meter. That way we can track our tuning progress. Start at the right height. A little more. Yeah, we'll grab. We'll use what. Right, that'll work. Those outdated computer chips are still good for something. And we're getting a whole 20 milliwatts. Exciting. 20 milliwatts from 10 amps. That's sufficient. Let's go see what we can set the LBO at. The output power should go up rather significantly. Ooh. The smell of current. There we go. Forming. 30 milliwatts. We're going to take a look for the peak output. Basically, when I just sweep the temperature range of the LBO, 50 milliwatts. And there will be a couple of points where it's going to get brighter and dimmer as the crystal finds its set point. We're going to see what the optimal set point is, and we're just going to run it there. 3, 2. Yeah, the 50 milliwatt range might have been it. Sometimes there's more than one range, so it's nice to just do a wide sweep when you can. Yeah, it looks like 50 milliwatts is what we're going to get right now. Which is rather sad. From 10 amps. You know, it's seen better days. Bring it up to the full 20 amps. See what we get. It should actually raise significantly in output. At the 15 amps, 500 milliwatts. Yeah, we gained some power. That's nice. I'll move this. Pretty nice spicy beam. Turn off the light. Ooh, yeah, that's significant output. I'd say go ahead and put something in the beam. See if it flams. 500 milliwatts, it should flam. Well, it'll smoke. Oh, yeah. Right. Cool. I'm going to turn down the current, and then we can take a look at the inside of the laser head as it's operating. And being a little bit careful on my end, not to go blind. Now there's probably a good IR filter on this camera. Let's see what we see. Blind camera action away. Yeah, there's not much IR to see with this camera at all. Turn off the light. Yeah, you can see where the IR is here off the pump diode. And here's the being passed for the 1064. That's really deep in the IR. You really can't see that. I think it's burning a hole in my wall. Is it? Will you get immediately brighter if I move you to a new spot? Nope. But yeah, looks pretty cool. I'll put the cover back on, bring it up to its full pump power. See what I actually get out of this laser at this point. 50 milliwatts, 60 milliwatts. Warmed up a little bit. All right, here we go. There you go. I added that in the power supply. Right here. I think I'm cooling the laser down too much. That should start climbing again. Well, as I said, it is a quite sick thin disc laser. It needs a little love and care. Probably optical adjustment and a new LVO. Uh, yeah. The most amount of output power I've seen out of this laser is about 900 milliwatts max, which is like half of what it should be doing, less than half of what it should be doing. So in that regard, kind of a disappointment, but still, I mean, not bad output power. It slams. Still very bright. And you can see the starburst on there. The starburst is incredible. It's a pretty coherent, pretty low line width laser as well. So it has its upside. It's a really cool laser. Now I might play around with this a little bit, see if I can get any kind of more output power out of it. But that's pretty much what I have to show you as far as what a thin disc laser is. There's not really much to tell you. All right, at this point, I spent a few more hours to try to get some better optical output from the laser head with marginal success. I'm going to go through this real quick because it's a pretty humid day right now, and I already have condensation starting to build up on here. I don't want that to build up inside the laser. These things don't like water, especially the LBO right here. Anyway, there's a couple of optical adjustment points that I picked up and I'm going to show you. So there's this screw here in the back. That sets the vertical position of the one positive meniscus lens. That is right after the thin disc. Got this adjustment screw here. That sets the vertical alignment for the high reflector right after the LBO. And then, of course, you have this screw, and that sets the vertical adjustment for the actual LBO, along with the two screws that I pointed out earlier, which sets the rotational adjustment or the horizontal adjustment of the LBO. And then this screw right here in the front by the output coupler, which sets the horizontal adjustment of that. So I'm going to turn up the power. We can see what kind of gains that I got, but I figured they probably drifted since I slept a few hours. So let's crank the current. I was getting 1 watt, so I was happy to see that. We'll see if that 1 watt comes back. Yeah, it totally isn't. Yeah, it looks like about 800 milliwatts is about the best I'm going to get from this laser. I'm messing around with the adjustment of the crystal temp just a little bit. See if that's what drifted. Hey, 90, I saw 90. Come on, you can break a watt. You can do it. I have faith in you. Yes, we hit 1 watt. We hit a lot. I saw it. It was there. It was there. All right. We do indeed have a watt of output, roughly. It's there. It is there. Not bad, not bad. Now that we have a 1 watt of output, go ahead and burn something real quick and then shut down the laser, put the cover back on so that way the moisture to get to it. Oh, yeah, this is a spicy bean now. Still not putting out full spec, but who knows? The LBO could be a little bit bad. The pump diode could be a little run. But yeah, no, fantastic laser either way. If you can pick up one of these for cheap, go ahead and do it. They're fun to work on. Pretty user friendly too. But yeah, that's about all I have for this video. I hope you enjoyed taking a look at the JenLas by Jenoptik, the wonderful thin disc laser. As always, I hope you enjoyed. Stay tuned for more.